Okay, so we are going to start with resting potential. The resting membrane potential of a cell is the difference in charges on one side of the plasma membrane versus the other. So here we see the plasma membrane, and we have the two different types of channels. So the charges come from ions like sodium and potassium. There are more sodium ions found in the ECF, or extracellular fluid, and more potassium ions found in the ICF, or the intracellular fluid. The difference is measured to be about negative 70 millivolts. It is negative because there are more negatively charged ions in the cytosol, or the ICF, than in the ECF. So the membrane is considered polarized. Even though sodium and potassium are both positively charged, we have these little, the little black ones represent the large anions, and they have a negative charge, and they are too large to escape the cell. Therefore, their negative charge counteracts against the positively charged potassium. So that is resting potential, the negative 70 millivolt. Okay, next up we have local potential. So only specific stimuli can open gates on ion channels. So we have a sodium ion channel here and a potassium ion channel here. And so when the sodium ion channel is stimulated and the gate opens, we see positively charged sodium ions move from the ECF into the ICF. This change makes the membrane less polar, and it is called depolarization. If the potassium ion channel is stimulated and the gate opens, we see that the potassium ions diffuse out of the cell, making it even more negative. So the potassium leaves the ICF and enters the ECF through the potassium ion channel. And this is called hyperpolarization. These are examples of local membrane potential because it only affects the immediate segment of the membrane. A few more things to know about local potential is that they are considered graded, which means they vary in magnitude depending on the strength of the stimulus. The more stimulation that occurs, the more sodium channels will open, which means more sodium ions enter into the ICF. They're also decremental, so this means the current gets weaker the farther away you get from the site of the stimulation. And then the third thing is that they are reversible. If the stimulation stops, the membrane will return to its resting membrane potential. All right, and our last step, action potential. Action potential causes a more dramatic change in the state of the plasma membrane. It can occur at the axon hillock and along the axon's length. It will occur at either full strength or not at all, so it's an all or nothing reaction. It is non-decremental, so it's the full strength the whole way. So first step, we see the resting membrane potential, we're at negative 70 millivolts. Local potential at axon hillocks is strong enough to cause a current that depolarizes the membrane to a threshold value of negative 55 millivolts. So over here, depolarization begins when we get to the negative 55. Sodium gates at this point open, and sodium ions rapidly diffuse from the ECF to the ICF, causing the membrane potential to rapidly depolarize from minus 55 to 0 and then on to 35. So we see depolarization ends, repolarization begins. So we get all the way up to positive 35, and then it starts to come back down. So the sodium gates close and the potassium gates open, causing potassium ions to rapidly diffuse from the ICF to the ECF. The membrane potential now rapidly repolarizes as the exiting cations cause the membrane potential to become more negative, eventually returning to negative 70 millivolts. So we see here the repolarization, it comes back down to the resting potential of minus 70. Potassium gates close, and now with both gates closed, the potassium sodium pumps return the cations to their original locations, and that is an action potential.